We're going to start it. So I think the Edison, my co-host, will post the Dropbox link on the chat. So if you kind of register late, you can just go to that Dropbox, just download the material going to use for this webinar. So, and we will go, I will stop for a few times during the demo and then try to answer questions. Okay. So let's just start for today. So today our topics will focus on how to make sense of the measurements on your image. So assuming that you take all the time, effort to take the pictures by the end, when you try to do some analysis, you want to get some number from it. So we just want to make sure that you understand what that measurement means. And there's a lot of things can happen on your image that can cause trouble to your measurement. So I will see. So assuming we'll have the Fiji ImageJ open here, and we'll go to our material. We'll first go to the number 8, cell measurement. So I have 2 images here. I will first open the cell 8. I just drag this one into a Fiji. It will open. So this is a fluorescence image. Ready? So assuming we can go through some of the process we did in the previous the webinar. So let's say we get all the information, we save all the ROI of the cell here. So this is our cells. I will zoom in a little bit. So we identify the cells, and now we want to get some measurements from the cells. We want to compare with the different group of the cells. Okay? And all the measurements you can do directly from the ImageJ. You can select it through the ImageJ, the main menu, analyze, set measurement. Once you click on this, it will gives you this box. So basically, this is it for the ImageJ. That's all the measurement is built in inside the ImageJ. You can do the measure. If you want to do anything other than this, you have to write your own macro code, or you want to do your own things to get the value you need from those parameters. So normally what we will do is what I see from our users, that the mass majority will be size, the mean intensity, and the integrate intensity. The name is a little bit strange, but actually that means the total intensity. It's basically the value in the variable, the column, times the mean degree value. So let's say I check this 3. For those are the cells we measured, I want to measure, for each cell, I want to measure the size, I want to measure the mean intensity inside the cell, and the total intensity. I click OK. So we have a total of 15 cells in this image. I want to measure every single of them. So in the ROI manager, I just click measure. I click on this to give me the result window. As you can see, we have the index of 1 to 15. That's corresponding to the index here. That's the index of the cell inside your ROI manager. And this is the size, the mean intensity, the total intensity. There are 2 values. We'll just talk about those a little bit later. Let me check on my, the people said that the value is too low. Okay, I'll try to speak louder. Okay. So this is the parameter we ask it to measure, the size, the intensity, and the total intensity. So when we're talking about those the measurement, we know the intensity value is actually the arbitrary unit. Getting? There's no actual physical unit attached to it. It's just the intensity. Ideally, it means the intensity about how many photons you receive. Getting? But then actually the size, the area here, this is a size. It's actually attached to an actually physical unit. It can be meters, centimeters, millimeters, or micron or nanometers. So we actually need to know when we see the first cell, which is this one, number 1. The size is 28.12366. So what is the unit? Is that the millimeter square, micron square, or nanometer square? We want to check. Okay? So to check on this, we need to know what we call the pixel scale information. Because what we're working on is a digital image. That's actually just a matrix. In this case, a 2D area. Then we need to know for every single pixel, that's the basic unit inside this image, how big is that? When we keep zooming here, you begin to see those single pixels in the image. We want to know how big is this single pixel. To know this information, we're going to check is the image property. If you go to the image property, now it will show you for this image, our pixel scale is here. So now we know that every single pixel corresponding to about 0.14 micron. That's 140 nanometer. This is taken under a confocal microscope. So now we will know here, when the area is 28, what is the unit? That's the micron square. Okay. So we need to know this is the micron square. But sometimes you will say, how does ImageJ know what is the pixel scale of this image? Okay? Because by far, almost every single modern imaging instrument, they will save this information with the image itself. It's saved into something they call the metadata. And the ImageJ normally can read the metadata very well, as long as you keep it the raw data format. So let's change this. So sometimes, let's say I open another one, they call cell B. I open this one. It looks like the same. I open the ROI. That's all the cells we check. I check the set the measurement. I still measure the size, mean intensity, and the total intensity. Now I click OK. Now I do the measurement. Now you begin to say, if you still remember what's this in the results table, the mean intensity is still the same. It doesn't change, but actually the area changes. Okay? Actually, we can also open the cell A again, and I just measure it. It will add up to the. So we have a total of 15 cells. The 1 to 15 is the cell B, and the 16 to 30 is cell A. As you can see, the mean intensity shows up basically the same, 106, 106 here. And but the area changes, getting? It's because somehow with the cell B image, we lost the pixel information. Now I highlight the cell B, I go to the image property. As now you can see, it's a pixel width is just 1 now. It's just a pixel. Somehow when you're doing something either in ImageJ or doing some other software, you lost the pixel information. So now what it gives you is actually the area is pixels. Like this cell number 1, what is area? Is they have 1,445 pixels in it. Ready? But in the cell A, we keep the pixel scale information. Ready? So once we measure in the cell A, you will see here that we actually give it here the unit is a micron square. So first, when you do the measurement in the area in the site, you need to first make sure what is your pixel scale, and list the ImageJ, read it. Getting? And then the next question will be like, how do I know, like, is that always under the micron unit or the nanometer, the unit, or if somehow I lost the information or my raw data didn't give me the information, what can I do? Okay. So now we'll go to the part number B. I will close this. Go to the B, the pixel scale. So first, as I mentioned, almost all major software or the instrument company, when they capture the image, they store the pixel scale in the image. So the ImageJ can actually read it pretty good. So for instance, let's say this is A5X.CZY. This is captured from a Zeiss microscope. So if you just open that in the Fiji ImageJ, I just drag it into it, it will invoke something called the bioformat importer. I normally just uncheck everything. I click OK. It looks black, but we can just do a white this and the contrast. Okay. So this is a bright field image of some cell in the dish. So then we'll say, what is the pixel scale in the image? I will click image, property, and that's it. For this image, the pixel scale is 1 pixel corresponding to 0.645 micron. That's actually saved by the acquisition software on your equipment. Ready? That software will calculate it based on the objective, the camera settings you use on this. Ready? And generally, ImageJ can read this data very well, but I always suggest you just double check at the beginning to make sure you check this information on your acquisition software on the equipment, and then you open the image in the ImageJ, and then check it again. Make sure they match. But by far, I haven't seen any case that ImageJ read it wrong. Like for this one, the Flybrain, open it. This is actually a 3D stack, a Z-stack image on a fluorescence image on a Flybrain. If you go to the property, it actually not only gives you the X and Y, it also gives you the Z. So when you do the Z stacks, what is step you use to ask the microscope to move in each slices? It's about 4 microns. And those information stay with the raw data. And once you open in the ImageJ, as I mentioned, I also ask you to save it. Once you do anything, you save it as TIFF. Once you save as TIFF, it stores this information in the TIFF. So later on, when you open the TIFF file, it will keep this information here. So that's also one thing very good about the TIFF. So whenever you do this image analysis, I always suggest you to save it with TIFF. So not only the X, Y, Z information, even if you have a time series, like here we have a swimming algae, this is a time series. Just you can also do some normal time series in like a calcium flux. But once you keep it the raw data, you can always use the image property. It doesn't save the pixel scale, but actually in this case, it saves the frame interval. So it actually saves that we know that between each frame inside this, between one frame is 5 seconds. Okay. So you need to make sure at the beginning when you to process your image, it's always good. You found the raw image, you open in the ImageJ, you just double check. What is the pixel scale? Let's say it goes to this one. This is my image. I check in the pixel scale. Does this make sense? Just double check with the acquisition software to make sure everything is fine. ImageJ can read the pixel scale very well, getting? And then we began to do all the processing. Getting? Almost every modern imaging equipment, when they take the picture, they save this information. But in case, sometimes people, we have the user, I take the picture on a microscope, it's very old, 20 years old, that's sitting in the lab for a long time getting. And when I get the picture, it's either in the TIFF, in the JPEG, everything, I don't have the information. Then what do I do? Getting? You can still do something with it. Yeah, let's go back to the slide. Let's just say we have the size, the intensity. So the integrated the density is just basically total intensity. That's actually, we'll see, it's actually the area times the mean gray value. Ready? And for other parameters, especially for the ferrite diameter and the shape, the shape descriptor, we have some like the web link you can check. That's something that's very, it's once you get a mask image, you can use those to get some interesting measurements based on the shape that helps you to include or exclude certain types of the object you got. Right? And this is you check the pixel scale, as we mentioned, almost all the modern instruments can do it. But if your instrument doesn't give you this one, you can also get the pixel scale information. You just need to get what we call the micrometer slide, something like this. You can buy them from the store lab or any kind of the optical company. I think it's about as cheap as like $20, or if you want to buy a good one, it's about $100 to $200. So basically, it has a ruler, very small ruler. Then you can take a picture of this small ruler under the exactly same condition as you take your picture. I have to emphasize on that, exactly same condition, which means the same objective, same zoom factor, same turbulence, and the same camera billing format. Getting? And then you take a picture of this ruler. Then in this case, when we measure this ruler, all the measurement the ImageJ gives you is in pixel unit because we do not have any pixel information. And then we actually know what is the physical length in this ruler. Then we can calculate it back. So for instance, if I buy this one, something like this, this is I buy the micrometer slide. I take under my very old the microscope and the very old camera. I take a picture. I make sure I take the picture under exactly the same condition when I take the picture of myself. Then what I want to say is, I have this picture. I check my pixel property. As you can see, it's single pixel. We cannot get the pixel scale. But now what we can say is we can draw a line. Actually, I already draw it. I'll just show up here. I will draw a line from here to here, and I'm going to measure the length of this line. Just click measure here. So it will give you, this is the length of this line. And what is the unit of this length of this number now? As we know, it's pixel. It's how many pixels from this to this. But now we know, since we spend all this money, we need to get some more information. We buy this slide. We know that this is how long, what the physical length is, 1, 2, 3, 4, 5. So actually, each smallest deviation is 0.01 millimeter. So this is actually total of 0.5 millimeter. One of the smallest deviation is 10 micron. So we have 50 of them. So we have 500 micron. So now what we can do is we can actually calculate this. Let me see if we can find the calculator. So this length is 500 microns, and it's 953 pixels. So 500 divided by 953. So each single pixel corresponding to about 0.525 micron. So then I can go to my picture. I'm going to go to the property. Then I'm going to change it here. So now, then I measure this again. Now this 500 corresponding to micron units now, because I already changed the property. And as you can see, that is 500 micron. So either when you get your image, your raw data containing the pixel scale information, or if you cannot get the pixel scale information, you get a micrometer slide. You can buy one, you can borrow one. That's if you have any kind of the imaging core around. Then normally the core have something here for the calibration purpose. Getting? You can buy one, and then you take a picture. But remember, you have to take the picture under the exactly same condition as you take your image, and then you can actually calculate what the pixel scale is. And once you get a pixel scale, then all your measurements, especially the size, makes sense. Like also, if I go to the FlyBrain here, we know what the pixel scale is. And if you want to put a scale bar in it, you can go to the Analyze tools, the same where you found the ROI manager, there's a scale bar. So the Analyze tools scale bar, and then you can add to say, I want to add every 100 micron scale bar. I want to put it into upper right position. I don't think the ImageJ has a very good scale bar function. It's just a very fundamental, just to draw the line here. If you want a better scale bar, you should be able to do that in other software or in the Photoshop. But as long as you know what the pixel scale is, you can add the scale bar in any other software. Okay. So I'm going to quit the, I'm going to check the chat, and let me see if you ever just take some quick questions on this. So again, just some people ask about the micron scale, the pixel scale. That's so one thing on this is that it actually doesn't matter on your analysis part, because in the analysis, we only work on the digital images. It's always pixel scale. So even though you don't know your pixel scale, you can still always do all the measurements. You only need to get the pixel scale by the end, and then you can convert all the measurements in the side, convert it to the physical length. Getting? Because that actually when you do the analysis on the digital image, it's all pixel based. You only need to think in the sense of the pixel by pixel. Just by the end, when you actually measure the size, we want to know what's the real physical size it is. So we're just we will continue on this. So let's go to part 6. So we talked something on in the first of the webinar. We mentioned that the thresholding is everything. So that's not only true for if you use the ImageJ, getting. I mean, thresholding, or we call the segmentation, is the fundamental, is the centerpiece for the digital imaging analysis. Everything depending on that. Once you begin to do more imaging analysis, you will realize that everything depends on that. All the measurements, everything. Okay? All your goal is that you need to work hard to try to get a good threshold holding. So now let's say I have this image. Okay? If my goal is try to identify the cells in the image, and I actually want to measure the cell just by the size. Let's say we don't even talk about the mean intensity. I just be by the size. And you'll be realize that the imaging size depending on how you set the outline of the cell. And when you use the algorithm, use the thresholding to get this cell, the outline change gradually based on the thresholding you're setting. So basically, let's see here. Let's say I want to go to the adjust thresholding. So if I change the thresholding, go to the lower one, you will see the cell, this part, like for this cell, it's getting smaller and smaller and smaller. So when we do the analysis, we try to make one value thresholding we consider is the best. And how do you know it's the best? There's no rule on it. It's a pure personal choice. If I say I think 110 here is the best thresholding. Okay? And you may feel 105 is the best thresholding. I do not agree with you. I think 110 is the best. You ask me why. There's no why. I like it. That's just my answer. Getting? And always people will think about you always should have some objective kind of a standard to decide. In this case, it's actually not. It's just the user, the scientists who are doing this, you need to make a choice. You need to decide which thresholding is the best. I think the 110 is the best. Okay? Why? Because I can show you this is a very nice representation of all the cells. Okay? But if you use the different thresholding, you will see the cell size changes. Okay? And we actually have, if you put this, the zip file into this, I actually have a different outline of this cell by using different thresholding. So this is if I use the thresholding 90, as all the pixels inside this outline has intensity higher or equal to 90. This is 100. You can see it's getting smaller, smaller, and smaller. Okay? So when we measure the size, you will see the size getting also smaller, smaller, and smaller. I deselect this. Let's say I only measure the size. I don't care about intensity. I measure it. So this is the size. Sometimes you want to make it clear. You can, when we set up the measurement, you can also show the label. Display label. So now when we measure this, you will say which one corresponding to which label. So we'll say when we set the thresholding as 90, the cell size is the biggest. That's the cell size is 637. And what is the unit? And we can check. This is the pixel. Once you see it's just the full integer number, you'll know that we lost the pixel scale in this picture. So that's just how many pixels. And then when it goes to even higher, the threshold holding goes to the highest. That's the size is 429. So if you actually compare the thresholding 90 and the thresholding 130, which is the first one, and the last one. Okay. The difference, 637 over 429, that's over 50% difference if you use this one over this. That's a huge difference. And we'll actually measure the same cell. All the difference caused by we use the different thresholding. Okay? And to make these things worse, you think about it, you look at these two selections. It is kind of, at least I can argue, those are reasonable choice. Sometimes you may say, I get a cell, just the size is too small, it's not realistic. You say, just not right. You look at outline for the cell, it's not right. But actually, if you look at all those selections, some of them you may say it's a little bit smaller, some is a little bit too big, but they are all reasonable. Okay? And all those kind of the reasonable choices can give you huge difference on the measurement. That makes your measurement very hard to believe. At least at first you want to persuade yourself. All my measurement is true. I can use to compare to gain some real knowledge, to do some conclusions. But now if I go through those thresholdings, even on the simple measurement of the cell size, I get huge different results, and they all look kind of reasonable. How do I know that my measurement is right? Unfortunately, in a sense that you can't really solve this problem in my point of view. You can't really say which one is the right one. There's no way to tell it. It depending on your choice. Okay? But what we can do is, once I set 110, as I said, I think this is good, then I have to use the 110 on all the cells. Not only all the cells inside this image. I want this 110 on all the images I get under different conditions. So the idea is not, is this a right or perfect measurement result from this single image or this single cell? The important thing is, if we can set up a protocol or process, a group of steps, we will fix on this process. So all the measurement we get is consistent. I think this is a very important kind of the people should be pay attention, especially on the fluorescence, the image analysis. It's always consistent. It's more important than what you think is the correct or perfect measurement in a single image. Okay? So we can say, you can say 90 is fine, 110 is fine, 130 is fine. But if you choose 130, I have to use this thresholding on all the images I capture. Then I will compare the size difference. The size of cell under condition A and the size of the cell under condition B. I say in the size of cells in condition A is bigger as long as they show the statistic significance. Okay? What I say is I use the exactly same thresholding 130 on all the images. Then the result shows me the statistic significance of the condition A has a bigger size than condition B. I will say, I will trust it. I think it is reliable. Okay? It's not because I'm so confident the 130 is better than 110. It's because when I choose the 130, I say to make a reasonable choice on the cell size, and I keep it the same, apply to all the images. Then it shows me the statistic significance between two groups. Then now I think the result is more reliable when I say these two groups shows the difference on that. So this is one thing I want to emphasize. I think many times people they try to work too hard on individual images to say this is what, as a human, you see, my very subjectively choose an image. This is how the cell outline is. Getting? That's in my point of view. Sometimes it's just a waste of time. You should focus is on to generate steps, how you want to analyze your images, to set up the protocol so you can work in this protocol on different images, on a group of images that they all make sense. At least on majority of them, they give you a reasonable result with the same parameter settings. And then we use the same parameters apply to all the images, getting? And then we'll see any difference show up between different conditions, getting? That will be the most important thing on your measurement. So people ask like, what's the difference between thresholding and the segmentation? To me, they're the same. It's just you separate the pixels in your image between different groups. One will be our object, one will be the background, getting? So once you separate them, it's much easier for the computer software to generate the outline of your object. Some also that if I have variation between our slides, we're having the same thresholding for our slide be the best option. That is the question, and that's many times is the problem, getting? So first we'll say that not only when you analyze your pictures, you have to use the same, exactly same protocol. You also need to make sure when you take the pictures, all the slides are under exactly the same acquisition condition, like the laser power, the detector setting, the camera sensitivity setting on that. But sometimes we'll see different sample, the control sample and your experiment condition, they are just different. The background will show up different, getting? The same thresholding just doesn't work. Many times they doesn't work, getting? In that case, you need to set up sometime what we're called, we plan to do that later in next, the webinar, just to focus on the thresholding, the method, that you can use some algorithm-based method to get the thresholding. We do not use the exactly same value. So different image, we use the different values. But we can say we use the same algorithm, so we can still say we treat them the same. Okay? It's not as perfect as you use the same exact values. But in many cases, that's the only way we can do. Some ask, how should you then report the measurement taken knowing the pixel size of the microscope and the setting used? And that will be your decision. I think that's in terms of the pixel size, that's even it's in the pixel case, because depending on how you draw the ROIs, it also gives you like the error actually here. It can be something called the 637.5 pixels, but that doesn't really matter because most of the time that your object is pretty big. So don't really care about the decimal point on the pixel size part. And so for the example A to C, I just show you something about when you make the measurement, you need to know what exactly you're measuring. One thing is to check what the pixel scale is, yeah, getting? And also just to understand by how you process your image, how do you decide, how do you draw the cells? The measurement can vary a lot, even under the same cells, getting? So you should be very careful. Getting? You need to make sure you set up a rule, set up a protocol, you follow it strictly. So all your image, all your measurement, you're getting it, even though it's pure under your personal choice. Many times it's very subjective to what is the best to identify the cells. Getting? Even it's very subjective, but as long as we keep the same rule that all the measurements are taken under the same condition, under the same rule, so we can still reliably to compare them. Ready? That's a more important thing. Make sure that your measurement, all the measurement coming from a consistent way. So I will keep going to the next part, which will be many things can happen to your image. So when you, even though you go through your images, getting, you take, you said, I get all the, I write down all my steps, how I'm going to process my images. And quite something can went wrong. You just need to be very careful. So I just show you some examples. So let me go to the be careful number 1. So let's, I open the weak cell. So this is my cell. It's kind of weak. Getting? That can be many reasons. That's when we take the pictures, we do not take it under very the optimal condition, or sometimes it's just the signal is weak just because of the sample. This is the best you can get. And we try to analyze the cells. I have the intercell. So this is my cell. So now let's say I want to do some measurements. I want to measure the size and the mean intensity. And I click OK. And then I measure it. So this is all my cells. Getting the size, which we do not have any pixel information here. So it's just pixel numbers. Let's say mean intensity, as you can see, it's pretty low. It's only like a 5, 6 one. But sometimes when you try to process the image, I can use the adjust. I can make the image looks better, like a higher contrast, to help me to identify the cell, even like if I want to manually draw the selections. Okay? You can adjust the contrast, everything. It doesn't really affect your measurement. As here, if we say we reset it, let's just do it again. To make it simple, I'm just going to delete here. I only show up 5 of these cells, those 5 cells. I do a measurement. You can see the intensity is actually quite low, but I want to see more clearly what the image is like. I click the auto. Now you can see I see it much more clearly in the cell. And now if I do the measurement, again, it's 5. Sorry, I clicked twice. As you can see from here, compared to this, the mean intensity doesn't change. So when you adjust the contrast here, it doesn't really change your pixel intensity on your image. It only changes how it shows up in the microscope screen to help you to identify the cells. Okay? That's actually what it should do. Getting? Do not change the pixel intensity. It doesn't really change your pixel here when you do the measurement. Yeah. But let's say I do first I do a measurement here. But there's an apply button here. If you click the apply button, now everything changes. It actually changes the pixel scale based on the settings you choose here. Now I go through all this file. I do the measure. You can see the intensity goes way up. Compare the number 1 and can't highlight both. Number 1 and number 6 are the same cell. They're the same size, but you can see the intensity changes. That's because you click the apply. Okay? Normally, I strongly suggest do not click the apply unless you know exactly what you are doing. Okay? You click this one, you change the pixel intensity. Many times in a very unnormalized way, you can't really get it back. Okay? You can play around. You can always play around. Go to the filter cell. You can change this, and we'll say use the auto shows up. It helps you to identify the cells, so it's much easier for you to just draw the cells. Getting, but whenever you are going to measure it, go back to the raw image, measure it. Getting, do not click the apply. Unless the only thing I will do in apply is I will create the apply, then I save the image. Like here, I save it as the adjusted one. Then I load it into my PowerPoint. I want to show just as a display to show people what the cell is. I'm not going to do anything measurement on this because I know all the pixel information is modified. It doesn't represent the true information when we take the picture. So this sometimes you just need to be careful. Sometimes when you check the image, you may sometimes you didn't realize you click the apply, and then when you run the image, the intensity level, you will see the intensity change a lot. And another thing sometimes happens is the images, the bit depth. So here I have two samples. This is cell A. I open it. We already see that's the, and this is my cell. I want to measure the size, mean intensity, and I see the total intensity. I measure it. So we have a total of 15 cells. Each cell we have the size, which now we know we can quick check on the property. That's the micron square. This micron square. This is the mean intensity of each pixel. That's the total intensity here. And then let's try to open another one, cell B. It looks like the same thing. I apply ROI on this one. Now I do a measurement. Now we compare the cell 1 and the number cell 16. They are the same ones. You will see the intensity changes a lot. The size is basically the same, but the intensity, the mean intensity change hugely, almost like 200, 100 times. Ready? So the reason for this is when you see the image, it doesn't really look much different. The reason is if you check on the image here, this image is an 8-bit image. And the cell B is a 16-bit image. As by the definition, the 8-bit image, our intensity level is between 0 and 255. So if I move to the cell here, and when you check the pixel intensity at here, this is about 130, 190 range. But when I go to the cell number B, the same region, we're looking at 47,000 the pixel. It changed how the detector on your acquisition system, your camera, your detector, how do they digitalize the signal? So many times that if you look closely, if you're doing the confocal or use the CCD, in the acquisition software, there are choices for you to say what the output data is. It's 8-bit, 12-bit, 16-bit. For the camera, you can also choose what kind of format the camera you want to use to take the picture. If you don't pay attention to that, sometimes it can be changed. but you don't realize it. And once you take the picture, it looks like the same. When you open the image, you probably won't see any difference here. Then you keep all your protocols to do the measurement. You will find on one condition, one image, the total mean intensity is way bigger than the other. That depends on what your intention is. What is your goal? Like your hypothesis is. If this actually match your hypothesis, you probably are very happy, and then you don't want to invest it more. Sometimes it seems strange. Why say that much? But if this prove the hypothesis, you will say, okay, that just prove it. I will take it. If it's actually against your hypothesis, you may think about, hey, maybe something's wrong. I'm going to check more. Then you realize it's actually one is a 16-bit, one is an 8-bit. So it just we actually see people that are the users. It happens when they're doing the confocal image. Somehow the setting changes. So for starting from sometime, their image always becomes to 16-bit. Then that causes a huge problem. Getting. But the good thing is that that user, he's actually very careful, and he very carefully check on the data. Then they realize something is wrong. Getting. Then they go back to change it. So this is something, even at your acquisition software, you need to make sure when you take the picture, it's under the same condition. That makes you need to really understand when you take the picture, when you analyze your image, you need to really know what you're doing. If you're not careful, that many things can happen. And it's not that easy. You just open the image in the ImageJ, you look at the image, you say, okay, that's the right one. That may not be the right one. Getting? That many things can change between that. And then the last example on the be careful is it may not happen to you, but it actually happens. What can I say? It's sometimes you get an image, it's just strange. I don't know why. Sometimes it's just for the biology samples when you're taking under the equipment, it won't happen. It happens when you try to use so many like software. Sometimes I want to do something, I don't know what to do it, how to do it. Then I go to search on the Google. I go to search, then I found something free one that seems can do it. So I download that one, I play around it, I open my images, I try all the things, and then it may not work, it may work, and then once I save it, and I don't exactly know what it does to my image. Some software can do very strange things on your image, and you can't really even notice it. This is just one example. So this one, if I go to if I open a normal one, this looks just an image. Then I open a strange one. I'm not sure if it will work exactly the same on your computer. It seems to also have, depending on the specific computer setting. So I would say it looks like the same. So now I'm going to do is I'm going to set ROI in the bright region. I add it to the ROI. Then I also draw another one in the black during the T shape here. So in a normal one, let's say, I measure it. As you can see, the mean intensity, the first one, which is in the bright region, has intensity of 243. The black one, the region is about 64. That's normal. This is bright, this is dark. But then if I go to the strange one, I highlight both. Now I do the measurement. Now you'll be able to see. This is the bright one part. This is the black part. The black part actually has a higher intensity value than the white region. Okay? And that is very strange, okay? When you first say that. Okay? But then when you actually check on the intensity value and move into here, you can check intensity at here. You will see it has a huge variation through it. Like here is 154, then it's 58, and also here we have 153, and sometimes it's only 55. And then move into the normal one, that is more consistent. Intensity is about the 63, 60 something, and in here, in this region is close to 240. So the problem with this strange image is, if now I ask it, force this one to show me what is real in the grayscale. I go to the image lookup table. I will say I force it to show me in the grayscale. It will say actually it's like this. If actually dark pixel showing up black color, bright, stronger pixel showing up white color, it will be something like this. Something changes on the image, getting? But when we open that in the ImageJ, we didn't see it because it has something stored in its metadata. It's called the lookup table. You can see the lookup table by the image you open. You go to the color, show lookup table. This is a very strange lookup table. This basically store with the image to tell the software when open it, what kind of color you shoot based on the intensity value. A normal image lookup table should look like this. Lower intensity showing up black, higher intensity showing up white. But here it has a very strange way to do it. This normally won't happen when you're using some kind of the imaging equipment. It happens when you try to use very software you do not know what they're doing and you apply to your image. Okay? And then you try to begin to do some measurement on those processed images. That may cause you trouble. Okay? So I guess when you open an image, probably I will assume at least 95% of you will never check this one. What is the lookup table? We just assuming when I open it, when it shows up bright, it's a high intensity. When it shows up dark, it's a low intensity. It's actually not the case in here. It happens rarely, but it happens. Getting? You just need to make sure that it doesn't happen to your image. One thing to avoid is that whenever you do the final measurement, always do it on your raw image. Getting? All your processed image is help you to identify the ROI, the region of the interest. For most of the time when we show the sample is in the cells. But once you are going to do the measurement, you apply the region of interest to your raw image, then do the measurement. That will save. So I have some users ask like what causes to happen. I don't know. It must happen. You through some kind of software. They cause it. They change the lookup table. For this specific case, I think they intentionally to do it to show the example. Yeah, getting? You can actually, they design the lookup table to show this. Getting? But many times if you use a software, you do not know what it exactly do, then it may cause trouble on it. So the same thing for all the imaging analysis and also same as you do the imaging acquisition is. You need to understand your sample. You need to understand your image. You need to know exactly every single step when you're doing what happened to your image. Then you can prevent those kind of the pitfalls in the imaging analysis. So even though it's 3, I just want to go through the last example. I use this a lot during my 3-day in-person the workshop. It's just a way that I will say. Now we see that the image can analyze the image can. It's actually let's close this one. You can close it. When they make the measurement, it can be a lot of things happen. You need to make sure you get the right measurement. But even if you get everything right, your measurement is correct corresponding to that. What actually does that mean? Sometimes can also cause trouble. Getting? You need to understand what exactly you want to get, what answer you need to say that what happened to this sample. Okay? So let's say if I have an image like this, all we need to know is we want to measure for this one, we can identify all the cells. What we want to measure is the cell size and the mean intensity inside the cell. And we want to see if the experiment condition has a higher or lower mean intensity compared to the control condition. That's probably about one of the most simplest comparison measurement we can think. We have a group of cells, we identify the cells and measure the cell size and the mean intensity. I want to compare between two groups to say which one is higher. So let's say I have this is my control group. I measure it, and I can do the measurement, something like this. I can measure the cell size. I can measure the mean intensity. But now, because we're going to compare this to another group, I want to pick up a value here to represent what is the mean intensity in my control group. And I use exactly the same protocol to do the same thing on the experiment group. I pick up the other value, then I compare these two values to say. But how do I pick up the value? I have 10 cells. I have 10 different mean intensity inside the cells. They're quite different because the cells, they have a natural variance getting inside this. So I will propose two methods. First one is I have 10 cells. I have 10 mean intensity. I get the mean of the mean. That's the mean one. I add up in the red box all those 10 values. I divide by 10. That's this value, 40.34. But I can also do another one. I can add another column. I use the size times the mean intensity. That's actually the total intensity inside this cell. So I have the 10 total intensity. I add them up. So I have the total intensity in all the 10 cells, and I have a total size of the 10 cells. Then I use this one divided by this. That gives me 39.5. I'm sorry, I think I made a mistake. This value should be green divided by this one. As you can see, these two values are quite close. It's very close. Normally they are, really, but they are different. Okay? It doesn't really matter which values you use. They probably give you the same result. But just for the sake of the argument, I want to take a poll if you can answer in the chat which one you're going to use, mean one or mean two, to choose this value to represent the mean intensity inside the cell under this condition. The mean one will be the mean of the mean, which will be this 10 numbers add up, divide by 10. And the mean two is actually, we add the total intensity of all the 10 cells and then divide about the total size of the 10 cells. So in a sense, what the mean two, what I do is I fuse all the 10 cells into a single big cell, then I calculate what's the mean intensity in this big cell. So our goal is we need to pick up a value to best represent the mean cell intensity in a control condition. Then I'm going to use this value to compare with another condition. So I see most people choose the mean 2. Anyone choose mean 1? I mean, through my years when I offer the workshop in the in-person 3-day workshop, when I talk about this, it's always, we normally have a very heated discussion on this. And people choose mean 1, people choose mean 2, that it's kind of hard to persuade each other. And my goal is not to persuade you, getting? My goal is actually want to show you it looks like a very simple question, but actually it's have quite something deep inside it. When you think about, we're just going to talk about the mean intensity inside the cell. And if you think about which one I should choose, it actually means a lot how much you understand your sample, what exactly what you need to do. Getting what is the measurement you should choose to fit your project into that. So first thing, as I say, the good thing or the relief things for all of you is that it doesn't matter which one you choose, they are always very same, very similar. The difference between this is way smaller than other error you can introduce. So no matter which one you choose, I don't think it affects your result. Okay? I want to say is that I will choose mean 2. I think this is the right one, but I can't really persuade other people when they choose the mean 1. So just at the end, I will just give you an example why I choose mean 2, and hopefully to see if I can persuade someone here. So I will use example in the basketball. Okay? So let's say if we go to the NBA finals, as you can see at that time, they are still in the NBA that I use this example for a long time. Okay? Let's say if you go to the NBA final game 3 on the final minutes, and then you will see that if the Lakers will always give the ball to the Shaq. So if you're the coach of the in the opponent team, that you will say that should we fall on Shaq or not? But that depends on how good is Shaq on the free throw line. Okay? And traditionally, that we know that he's not good, but maybe in this series he's just so good. And all the information we have is the data we get from the first 2 games. So let's say if the game 1, he only get 1 shot attempt, and he made it. So that free shot percentage, 100%. It's kind of abnormal static, the statistic, but that's what we got. And in the game 2, Shaq gets 12 tries on the free shot line, and he made half of it. That looks more like a Shaq. Okay? So now based on this 2 games data point, we want to project coming into game 3, what is the free shot percentage of the Shaq? So we have 2 ways to calculate it. We can calculate by the percentage in the game 1 plus game 2 divided by 2, which gives us a 75%. But we can also say, what we can do is we can get all the shots he made divided by all the shots he attempted. That gives us 54%. That's a huge difference. And I think I'm fairly confident to say in this case, I think you will agree this one, 54%, will be the right one to represent the free shot percentage of Shaq in this series. So my argument is if I compare this example to the cell, that the game are the different cells, These are the mean intensity of each cell. When we actually think about in a new game, that means coming into a new cell, what is the most expected mean intensity, which here we mean the most expected, the threshold percentage, we should use this one. We should use all the, we should like fuse these two games into a bigger game, and then we calculate it. Okay? And I would say, if you compare to the Shaq's career, the average, there's actually more close to that. As I mentioned previously, I do not intend to use this one to say the mean 2 is right. To be honest, I actually never really understand, like can convince myself that the mean 2 is right, the mean 1 is wrong. I will use the mean 2. I argue this with a lot of people through a long time getting. I think once people make up their mind, it's very hard to change it. This just serves as an example to say, even very simple concept in the measurement, it can be mean a lot of things. You need to be very careful. And I hope for this, the, the, the webinar, you kind of get a feeling when you do the measurement, many things can happen. You have to be very careful what you're doing. You need to understand what you're doing to make sure the measurements, the results, the value numbers you get are consistent. And it actually truthfully reflect what we coming from the data from your sample. Okay? And again, we will send out, so this will be the end of the webinar. We're going to send out notice very shortly. The next one will be focused on the thresholding and the segmentation, as we mentioned. That's actually the centerpiece of all the digital image analysis that deserve just one webinar, just talking about that. Okay? And also this seminar is recorded. We will post the link on our website very soon. And we plan to also begin to upload some short instruction videos on the specific topics on the ImageJ very shortly. Okay? And I hope this helps you to also like promote you to use more the ImageJ. I think it's a very good software through the years. It's free. As a scientist, we should always kind of promote those free share open source one. So this will be the end of the webinar. Thanks for coming. I will just wait a few minutes just to see if anyone has any questions I can answer. Thanks. About the ImageJ macro programming, I think that one I do not think is the right format to do it online, but I do plan to put on some like shorter videos to put on our website that will go through that step by step how to begin to write a macro language, and we hope we can put this online pretty soon, before the Christmas. Okay, if there's no more question, we're going to end the webinar, and you are always welcome to contact me directly through email if any questions about specifically on your imaging process project. Okay, thanks.